From this video, we'll start talking about two-dimensional continuum. Just like strain in the continuum bar was motivated by strain in the discrete truss member, for the 2D continuum, we will motivate strain using a discrete approximation by triangles. So let's consider some kind of an arbitrary 2D continuum object whose undeformed configuration looks like this, with coordinates represented by uppercase letters. And its deformed configuration looks like this, with coordinates represented by lowercase letters. And the deformed configuration is given by the functions x hat and y hat, and the displacements u hat x and u hat y. So we approximate this continuum by a patchwork of triangles. We divide the continuum into triangles as an approximation, and we assume that as the object deforms, the edges of the triangles remain straight. So as the number of triangles, so that's an example of one triangle being deformed into this triangle. So as the number of triangles is increased, this approximation slowly becomes closer and closer to the continuum. So let's take one triangle, for example. Suppose this triangle has these coordinates 0, 0, 2, 1, 1, 3 in the undeformed configuration. Let's label these two sides 1 and 2. And in the deformed configuration, let's say that the coordinates become 1, 1.5, 2.51, 1.54. So let's define a matrix uppercase D uppercase X, which consists of the two side vectors, x2 minus x1, y2 minus y1, x3 minus x1, y3 minus y1, which in this case is 2, 1, 1, 3. And the side vectors in the deformed configuration, d lowercase x, like that, which in this case is 1.5 minus 0.5, 2.5. So we ask the question, what is the matrix that maps the side vectors in the undeformed triangle to the side vectors in the deformed triangle? Let's call this matrix uppercase F. So d lowercase x equals this matrix F times d uppercase x, from which we can get F equals d lowercase x, d uppercase x inverse, which in MATLAB we can write as F equals dx right divided by dx. So this dx by dx looks a lot like the dx hat by dx in the 1D bar, and it's very tempting to define the log of this quantity as strain. But in 2D, we also have to account for rotations. And we'll see how to do that in the next few videos. In the meanwhile, this matrix F is called the deformation gradient.